If you combine superconductors with magnetic fields, you get some nice interesting effects. I mean, I had another interesting one, but I couldn't find it. This is also not bad. These are all magnets. So there's a rod made up of magnets. This is a superconductor. Well, inside there is a superconductor, let's say. Now, the superconductor doesn't have any resistance to the current, so you can easily build up as high a current as you like in it. So and it is not being attached to this magnetic in any way. So it's just suspended by the magnetic field only. So if you just would follow it from, let's see. So the superconductor, it appears at very low temperatures, very close to, I mean, the highest temperature superconductor we have is like minus 200 degrees Celsius. So you have to really cool it down. So this is probably liquid nitrogen. So it pours liquid nitrogen to cool this superconducting material. And it's just putting it close to the magnetic field, and that's it. It's already blocked there. It cannot move away from the magnetic field. It cannot approach the magnetic field. It cannot go far away from the magnetic field. There is a resistance. There's air. I mean, this cart is not very small, so inevitably it feels some air resistance. It's not electrical resistance, but there's friction. So it just stays there. So it's just like having two magnets. I'm sure you have played with magnets. If you try to approach two magnets close to the north poles of two magnets, they will repel each other. If you just take the south poles, the north and the south pole, they will attract each other. Now let's see how that force arises. Not in the case of a permanent magnet, but for the time being, let's just assume we have loops, current-carrying loops. Well, unfortunately, the magnetic field of Earth is quite weak. Okay, on Tuesday there were a couple of questions about what is the north pole, what is the south pole of a magnet or of a dipole. So let's see, we have this wire, infinite wire. Now let's look at the magnets first. We say that, okay, this is the north pole, this is the south pole of a magnet. Now, if you would plot the magnetic field lines, these are how the magnetic field lines look like. So if you look at the magnetic field lines, they're not just out of the magnet, they go through the magnet. It's quite high in the magnet, in fact. So in fact, that is why we have, if you just cut it over here, still the magnetic field lines, they will start from here, they will just form closed loops. At one point, the magnetic field lines enter into the magnet. That is what we call the south pole. And at some other point, the magnetic field lines leave the magnet, and that is what we call the north pole. And there's still the magnetic field lines going through. Now, if you take an infinite wire, well, it doesn't really have a north pole or a south pole, because the magnetic field lines do not start at the wire, do not end at the wire. But if you, for example, just, let's say, this is I, you just imagine some volume. You can even imagine a hypothetical volume, just like this. Now, in that case, you can identify some north pole or a south pole. So let's say this is our wire. I just take this volume over here. This is the direction of the current. Now the currents, they will just go around. So the magnetic field lines enter from this point and they leave from this point. This is where we can say that, okay, this thing has the south pole over here and the north pole over there, if you would like to really give it such a definition. Well, in this case, it doesn't really make too much sense because this on its own doesn't have a magnetic field. Now, let's first discuss the Biot Savart Law. Not in much detail yet. In the next hour, we can go to the details. Now, the problem with our previous approach was that we always considered infinite straight wires. We don't have infinite straight wires all the time. So if you take an arbitrary wire, it is still carrying some current I. We can still calculate the magnetic field created by this wire, let's say at this point. Now what we do is we just divide this wire into very small segments. We can just take one of those segments, let's say this is our DL. Again, the direction of DL is in the direction of the current. And we can, okay, this is DL. This is, let's say, the position vector of that point at which we are trying to calculate the magnetic field relative to our DL. Then this piece of the current would contribute to the magnetic field an amount, let's say dB, which is equal to mu0 over 4 pi I dl cross r hat divided by r squared. Okay, again, it is current over r squared, just like in the case of the electric field. If you remember, the electric field was this 1 over r squared law. Here again, we have this 1 over r squared. And the charge, in a sense, is the current that is running through this link, and the direction is given by this cross product. Now, in this example, for example, where is the direction of the magnetic field at that point? Where is the contribution? It's inside the screen. So it's dl cross r. It is pointing, my thumb is pointing inside the screen. This is my dl. R is like this. My thumb is pointing inside the screen. This is the direction of the magnetic field. Yes? It's the unit vector. It determines the direction. If r hat changes direction, then the L cross r vector changes direction. Now let's imagine we have such a ring. This is the direction of the current. What will be the direction of the magnetic field? Okay, one thing is you can just wrap your fingers around the current, the magnetic field will be pointing upward. What will be the direction of the magnetic field over there? Okay, so just wrapping your fingers around these rings doesn't really work that much if you are not exactly on the axis. Now, but what you can do is you can just apply this Biosavart law again. We just divide it into very small segments. And then, well, even if you look at this point, let's take this segment. The L is almost into the screen. R hat is something like this. Okay, the L is into the screen. R hat is something like this, yes. Okay, this is dl, this is my r hat, dl cross r hat, this is the direction of the magnetic field from that segment. From this one, the contribution will be something like this. From this segment, the contribution will again be something like this. That will be the direction of the magnetic fields. Okay, this is our ring. This is my DL. The current is running like this. And I would like to find the magnetic field somewhere over here. Okay, what will be the direction of the magnetic field? Okay, so this is my DL. DL, R is pointing in this direction. This is the direction of my magnetic field. So this way. From this part, what is the direction of the magnetic field? DL is like this. R hat is like this, so it is this way. It is upward, it's not like this. It is upward. But nevertheless, that other point is further away, so the magnitude will be smaller. So the net magnetic field will still be pointing somewhat in the downward direction. Now, if you would plot the all of the magnetic field, this is our ring, this is the current. As your friend has said, okay, so let me just draw it also here. In, out. At this point, the magnetic field line will be just like this. Close to the rings, the perimeter, they will be just circles. Just wrap your fingers around the wire. That gives you, such that your thumb is in the direction of the current, it will give you the sense. So they will just, the circles will grow. So this is how the magnetic field lines of this ring will look like. So it will be just like small circles here, and as it goes away, it will get larger and larger. This is how the magnetic field lines look like. So if you would assign, now you can, this has its own magnetic field. Now it makes sense to assign the north pole and the south pole of this magnet. So what is the north pole, the top or the bottom? The top. The top is where the magnetic field lines come out. So that is your north pole. If you would treat this as a magnet, that is your north pole, and the bottom is your south pole. You see, the magnetic field lines out of the magnet, they just go from the north to the south. But if you take the magnetic field lines come out of the north pole. So if you treat this whole thing as your magnet, this is your magnet. So the magnetic field lines are coming from this side and they are entering through this side. Even here you see the magnetic field lines, they start from the north pole and they go to the south pole, but this is only out of the magnet. In the magnet, magnetic field lines go from the south pole to the north pole. So let's see what happens if we bring two such loops together. They both carry the current in the same direction. Will they attract or repel? Well, if you just use this magnet analogy, this is the north pole of this magnet, this is the south pole, this is the north pole of the other magnet, this is the south, no, sorry. This is the north pole, this is the south pole, this is the north pole, this is the south pole. So if you just use this magnet analogy, this is as if you are just bringing two magnets close together such that the north pole of one of them is closer to the south pole of the other one, so they should attract. I didn't understand. This is my loop. This is the direction of the current. So the magnetic field lines, they just start, if you just would pick some point, they go like this. Okay. So that is a circle like just like this. And this is the direction of the, this circle, that is how I can show this circle on the screen. No, I'm not, okay, just, okay. The north is here, south is here. It's not north and south. The north and the south, the top and the bottom. It's not the further away side and the closer side. Yes, it's a three-dimensional graph. Okay, so why does the north attract the south? Okay, we all know we all played with the magnets, and we all know that certain sides attract each other, certain other sides repel each other. But in this simple analogy, at least, how can we understand that? Now, this is something we can discuss. We already know enough to determine why they attract. Now, let's look at the force acting on the top ring. Okay, if we want to determine the force acting on the top ring, we first have to determine the magnetic field at the point of the top ring. This is my ring. Okay, so let's just say, let me just draw this one. This is the current, II. What is the direction of the magnetic field here? This point. Due to the other ring. Just look at this one. The magnetic field lines in the upper part, okay, they are mainly upwards, but they bend towards the left or towards the right. It will be the same thing over here. So this will be the direction of the magnetic field at that point, at that part of the ring. Now, if we look at this one, okay, the magnetic field will have, if they are just on top of each other, they have the same size. And then in that simple case, they will have this will have the same magnitude, but its direction will be slightly shifted to the other side. This will be the direction of the magnetic field over there. Now we have a current in a magnetic field. What is the direction of the forces acting on this segment over here? Remember, the force acting on a current carrying wire is I times dl cross B. On the left-hand side, I is pointing towards you, out of the screen. So dl is a vector pointing towards you. B has this direction. So this is the L, this is B, so this is the direction of the force acting on it. It is perpendicular to B, so it will be something like this. This is the force acting on that segment. What about the other one? This one. In this case, the current is running into the screen, so dl is a vector pointing into the screen. B is in this direction. It's just downward towards the right. And the sum, in which direction does the sum point? It points downwards. So they are attracting each other. Yes, now we are considering this top ring. This is this part, this is the other part. The ring is just like this. So the top ring feels a downward force. Well, let's repeat with a different setup. Let's just assume that, okay, we have the same system almost. Yes. Now, if this is the case, this is the north pole, this is the south pole of this magnet. Now, again, just playing with the magnets, we already know that there should be a repulsive force between the two. Let's just calculate it. Now, this time, this is the current going down, this is the current coming up. What is the direction of the magnetic field over here? Magnetic field at this point due to this ring. I already put the point over there. Well, I didn't change the magnetic field. I mean, I only changed the direction of this loop. Of course, that loop is creating a magnetic field in the downward direction. But the force that this loop will feel will be due to the magnetic field created by this ring, which I didn't change. So the magnetic fields are still the same. It is in this direction on the left, on this direction on the right. Now, what is the direction of the forces? On this part, this is our dl, this is B, this is the direction of the force. And on this one, this is the direction of dl. Okay, this is the direction of the B, so it will be in this direction. So the net force will be just pointing in the upward direction. So the top ring will be repelled from the bottom ring. Now let's look at the magnetic field lines in both cases. This is case 1. This is case 2. How do you think will be the magnetic field lines? Well, very close to the rings, nothing will change. As you go away from the rings, they will start to get a bit deformed. Of course, at every point there is a line. Now you can just think of it as if, okay, every dipole, you can just think of it as if it is sucking magnetic field lines from their south pole and spitting them out from the north pole. It's just like an attractive force for the magnetic field lines. So if you look at here, it's trying to attract, they are all trying to attract the magnetic field lines. So you can just imagine that there are these strings connecting to the strings that are pulling them together. Now, if you look at this other configuration, though, what will be the magnetic field lines look like? At the very close, there won't be any difference. You see, the bottom ring is trying to spit out magnetic field lines from the top. The top ring is trying to spit out the magnetic field lines from the bottom. So they will be pushing each other. Just imagine them as if they are a fluid flow, they will be just pushing each other. So the magnetic field lines will be significantly deformed as they approach each other, and somewhere over here they will just go like this. This is how the magnetic field lines will look like. Now let's put the arrows. So just by looking at the magnetic field line, the shape of the magnetic field lines, you can just determine whether there will be an attractive force or a repulsive force. So if they just go through all of the systems, then there will be an attractive force. If they collide, they tend to collide, then there will be a repulsive force. Here, as this magnetic field line goes up, they seem to be colliding with the magnetic field lines coming from the top. There won't be any collision, they will be just pushing each other away. Any questions? Somewhere over here. Let's calculate, if there is such a point. Now let's first start by calculating the magnetic field due to a single ring. Now here, because we know that at least along this central line, well, at every point, there will be let's say from the bottom ring, there will be a contribution to the magnetic field that's pointing upwards. And from the top ring, there will be a contribution to the magnetic field that is pointing downwards. So if we can just sum the two, we can determine the net magnetic field at any point along this line and see if there is a zero somewhere. So we have this single ring. It's a three-dimensional plot. And we would like to find the magnetic field somewhere along its central axis. This is the point P. Let's say it has a radius R. We are at a distance D. And we have a current running through it. Well, as usual, we know the Biosavart Law. If we just divide the loop into very small segments, we know that the magnetic field created by each one of that segment will be mu0 over 4 pi I dl cross r over r squared. This is the contribution of each one of the small segments. And then we need to sum them all up. Now let's see, let's take a small segment somewhere over here from the extreme right. What will be the direction of the magnetic field created by this segment on the extreme right at that point P? Okay, first of all, DL. DL is pointing inside the screen. Let's look at R. R is this vector. R vector is on the screen. DL is pointing into the screen. DL cross R, upper right. So that is the direction of the magnetic field created by this small segment. Now we can consider the symmetric segment. Well, no, let's just stick with this one, dB. Yes, dl is always in the direction of the current. What is the magnitude? Okay, it's mu0 over 4. Okay, sorry, this is r hat. Mu0 over 4 pi I times dl. R hat has unit length over r squared. What is the angle between dl and r hat? It's 90 degrees. One of them is into the screen. The other one is on the screen. 90 degrees. So cosine of 90 is just 1. Sine of 90 is 1. And in the cross product we have the sine. Okay, so let's write this dB vector. It is its magnitude. Let's just call this angle over here theta. It is dB times cosine theta. Let's say this is the z direction. In the z direction, plus dB times sine theta in the, let's say, x direction. Now I have this vector. I define this angle to be theta, so I just write the components of this vector dB. I said this is my x, this is my z, this is the vector dB, this is theta. Now let's look at this segment over here. What is the direction of the magnetic field created by that vector, that segment? Well, the dl vector is coming out. R vector is like that. dl cross r, it is in that direction. It is symmetrical to that one. So it will be in this direction. And furthermore, their magnitudes will be equal. I'm just assuming equal length of the ring, so their magnitudes will be equal. Now we already wrote down dB. dB prime will be dB times, this is also theta, dB times cosine theta in the z hat plus dB times sine theta in the x minus x hat. So they have the same component in the z direction, but in the x direction, one is in the positive x direction, one is in the negative x direction, although they have the same components, same length. So when I sum them up, there is only the z component that is left. So that is the only component I have to keep track of. So dB is equal to mu 0 I over 4 pi dl over r squared. Now this angle over here is also theta. So cosine theta is nothing but r over small r. This is my cosine theta in the z direction. Plus the x component and the y components. But they will. This is my small r. Here. Okay, it is the magnitude of r hat, which is 1. So this is dB. Of course, it also has the x and the y components, but we already have seen that they will cancel each other when I consider the sum. Now, to calculate B, I have to sum all of them over each one of these small segments around the ring. Now, let's see. As I take different segments of the ring into account, mu 0 will be the same for each one of the terms. I will be the same, 4 pi will be the same, r will be the same. Every point on the ring is at the same distance from that point P, 1 over r cubed. R is the same, z hat is the same, and then I have the sum over all of these dLs. But when I sum them up, I get the circumference, which is 2 pi r. So this is my magnetic field. Which will be equal to mu 0 over 2 pi times mu over r cubed in the z hat direction, where this mu is pi r squared. Now, if you remember, we defined this magnetic dipole moment when we were discussing the torque acting on our loop. And the magnetic dipole moment we had defined as the current times the area. This is the current running around the circle of circumference r, so pi r squared is the area of this circle. But pi is over here. In mu there's a pi. That is how I define this mu. No. You see, I mean, the previous example, when we had this rectangular loop, the area was A times B. Here, the area is pi times r squared. That's why I keep the pi in the definition of the magnetic dipole moment. You see, cosine of theta is small r over large r. Here I have this right triangle. Theta is this angle over here. Now I can even write it in another form. Let's say this was the example we have. We have this ring. We are looking at this point over here. What is the direction of the magnetic dipole moment of this ring? Upward, because the direction we define by the right-hand rule. Just wrap your fingers in the direction of the current. Your thumb points in the direction of the magnetic dipole moment. So this is our magnetic dipole moment vector. So the magnetic field, we can even write it in this form. It is mu0 over 2 pi mu over r cubed. It's in the same direction as the magnetic dipole moment. At least it's in the same direction along this central axis. Now this R, now if you look at here, this R is also given as, we can also write it as square root of d squared over plus large R squared. So this again becomes mu0 over 2 pi mu divided by square root of large R squared plus d squared to the 3/2. Okay, if you just remember the expressions for the electric field created by an electric dipole, it also has exactly the same form. The only difference is instead of mu0 we have 1 over epsilon 0. That's the only difference. They behave identically. No. They have exactly the same form, not the same value. Now let's go back to your question, whether is there a point in this configuration. Where there is a point where the magnetic field is 0. Assuming both of the rings are identical. Now, if you look at the expression, the only thing it depends on is the distance. Now, this d is the distance from the center. So the magnitude depends on the magnetic dipole moment. But if you look at these two loops, they have the same circumference. And they are carrying if they are carrying the same current, then their magnetic dipole moments are equal. And if you take a point that is at the same distance from both of them, in the middle, at this point, B is exactly equal to 0. Because from one of them, this one has this magnetic dipole moment pointing upward, so the magnetic field of this loop is pointing upward, whereas the magnetic dipole moment of the top loop is pointing downward, so it will create a magnetic field pointing downward at this point, and right at the center they also have their magnitudes equal, so they just cancel each other. So if you go back to the drawing of the magnetic field lines, you see that even if you increase the number of magnetic field lines, none of them will pass through the center. They will, for example, just go like this. Right at this point, there is no magnetic field line. Questions? Well, it depends on if the currents are slightly different, if you increase this current, this point will just shift downwards, but it will still exist. Not always. You see, the magnetic field right at the center of this one, it corresponds to when d is equal to 0. When d is equal to 0, the magnetic field line has some finite value. Even if you make sure that the other one, this one creates such a large magnetic field on this point, it will not be zero. And well, this point will just be pushed away and away. But eventually, if you take this current to be larger and larger, this point will move away and away towards infinity, but you will never go to infinity. Well, the problem is there is a velocity. It's not rotating. Okay, if it's not moving, there's no magnetic field. If you ask the question that you have this infinite plate and it is rotating around this point, then you can calculate the magnetic field. The magnetic field lines will just look like something like this. Okay, let's give a break and we will continue after the break.